Example number 2 for the simple Rankine cycle. For the actual case, the question states that a simple Rankine cycle uses water as the working fluid. The boiler operates at 6000 kPa and the condenser at 50 kPa. At the entrance of the turbine, the temperature is 450 degrees Celsius. The isentropic efficiency of the turbine is 94%. The water leaves the condenser as saturated liquid. The boiler size for a mass flow rate of 20 kg per second. Sketch the TS diagram and determine the rate at which heat is added in the boiler in kilowatt, the power required to operate the pump in kilowatt, the net power produced by the cycle in kilowatt, and the thermal efficiency of the cycle in percentage. Normally, for the actual Rankine cycle, the information that will be given for you is the isentropic efficiency of the device. In our case, given to us is the isentropic efficiency for the turbine. Therefore, we are going to find the actual values and we are going to use it to determine all the required items as requested by this question. This TS diagram representing the ideal simple Rankine cycle. However, we know that from the question, it gives us the actual situation for the simple Rankine cycle. However, in order for us to sketch the processes throughout the cycles, we need to really know what is the phase for each state, especially for the states leaving the turbine. For this example, let's have state 1 leaving our pump, state 2 before entering our turbine, state 3 before entering our condenser, and state 4 before entering our pump. In this question, they require us to determine the rate at which heat is added into the boiler in the unit of kilowatt. So this is actually referring to Q dot in. Power required to operate the pump in kilowatt. So this will be W dot in. The net power produced by the cycle in kilowatt. This will be the power net out, and it is equal to power out minus power in. And we need to determine the thermal efficiency of the cycle in percentage. So thermal efficiency for Rankine cycle is equal to power net out divided with Q dot in. If you notice, in order for us to solve these items, we need to find the values for Q dot in, W dot in, and also W dot out. From our TS diagram, power in is across the pump, which is process 4 to 1. Heat transfer rate into our system is for the process 1 to 2. And the power output produced by the turbine is across the process 2 to 3. From the steady flow energy equation, we can find the power in to our system by this expression. And for our case, referring to the TS diagram right now, power in will be equal to the mass flow rate times with the enthalpy of the pump outlet, which is H1, minus with the enthalpy for the pump inlet, which is enthalpy at state 4. Similar approach is going to be done for the heat transfer rate into our system, Q dot in. So we are going to get Q dot in equal to m dot times with enthalpy out minus enthalpy in. So in our case, by referring to the TS diagram, we are going to get Q dot in is equal to the mass flow rate times with enthalpy at the boiler outlet, which is state 2, minus enthalpy at the boiler inlet, which is state 1. And for the power output across the turbine, we are going to get the final steady flow energy equation is power output equal to the mass flow rate times with enthalpy at the inlet of the turbine minus the enthalpy for the outlet of the turbine. So based on our TS diagram, again, we are going to get the power output is equal to the mass flow rate times with the enthalpy for the inlet of the turbine is at state 2 minus enthalpy at the outlet of the turbine, which is state 3. In order for us to find the values for the power input, the heat transfer rate, inlet, and also the power output, we need to find the values for the enthalpy for state 1, state 2, state 3, and also state 4. The information given to us from the question is the boiler operates at 6000 kilopascal and the condenser operates at 50 kilopascal. Also given to us is the temperature at the turbine entrance, which is 450 degrees Celsius, and do not forget, we are also given the isentropic efficiency of the turbine, which is 94%. So we are going to list out all the informations given to us by referring to our TS diagram. So the boiler pressure is representing the pressure at state 2 and state 1, and the condenser pressure is representing the state 3 and state 4. The temperature given at the turbine entrance is 450 degrees Celsius, representing the temperature at state 2. And also given to us is the isentropic efficiency for the turbine, 94%, which is equal to 0.94. Note that the isentropy efficiency for turbine is given by the actual divided with the isentropic process. So by using the value for the isentropic efficiencies given, we can find the values for the enthalpy at state 3 for the actual case. And later, we are going to use these actual values in order for us to find the power output. Now let's find the value for the enthalpies for each states. At state 4, the phase is saturated liquid, and we have the properties is pressure, which is 50 kilopascal. From table A5, we are going to refer to the pressure equal to 50 kilopascal, since we know that state 4 is in saturated liquid phase. Therefore, the enthalpy will be equal to 340.54 kilojoule per kilogram. And we also can obtain the value for the specific volume at state 4. So then we can use this value later to find the enthalpy at state 1. Next, we're going to find the enthalpy for state 1, that leaving our pump and before entering our boiler. The informations that we have for state 1 is the pressure, 6000 kilopascal, and the value for the specific volume at state 4 is equivalent to the specific volume at state 1. We are going to use this equation in order for us to find the enthalpy for state 1, since we have the value for the enthalpy at state 4, the specific volume at state 4, the pressure at state 1, and the pressure at state 4. Next, we are going to find the enthalpy for state 2. We know that state 2 is in superheated phase. The information that we have is the pressure at state 2 is equal to 6 megapascal or equal to 6000 kilopascal, and the temperature is equal to 450 degrees Celsius. Even if we perform the characterization for state 2 by referring to table A5, we're still going to get the phase for state 2 is superheated. Thus, we're going to refer to table A6 for the pressure of 6 megapascal and the temperature is 450 degrees Celsius. The value that we are going to retrieve from this table is the enthalpy and the entropy. And lastly, in order for us to find the value for the enthalpy at state 3, first we need to do the characterization for this state, so then we know this state is in which phase. The information that we have is the pressure at state 3, which is 50 kilopascal, and also process 2 to 3 across our turbine is in isentropic process, where entropy at state 2 is equal to entropy at state 3. Since we now have two properties for the state 3, which is the pressure and the value for the entropy, now we can perform the characterization for this particular state. From table A5, we can see that the value of 6.7219 kilojoule per kilogram Kelvin is in between the value for the entropy for the saturated liquid and the value for the entropy for the saturated vapor. Therefore, state 3 is in the mixture phase. Before we can determine the value for the enthalpy for state 3, first we need to find the value for the quality at state 3. Now, since we have the value for the quality at state 3, we can now determine the value for the enthalpy for the state 3. Note that the value for the enthalpy that we obtain for the state 3 now is the value for the enthalpy for the isentropic process. Therefore, do not forget to write subscript S to these properties. Since we know that the isentropic efficiency for the turbine is 0.94, therefore we can obtain and determine the value for the enthalpy actual at state 3. Since we now have the actual enthalpy at state 3, we are going to perform again the characterization in order for us to know the specific phase for this actual state. It is observed that from table A5, the value of the enthalpy equal to 2394.3996 kJ per kilogram is in between the value for the enthalpy at the saturated liquid and saturated vapor. Therefore, the actual state is still in the mixture phase. Since we now have all the values for the enthalpies for each states, therefore we can solve for the items that is requested by the questions. But before that, I would like to highlight to you guys that it is very important for you to know the condition for each state. For example, at state 4, it is the state leaving the condenser before entering the pump. For state 1, this state is after the pump and before entering the boiler. And for state 2, it is leaving the boiler and before entering the turbine, while the state 3 is leaving the turbine and before entering the condenser. Since we have all the required informations, now we can solve for all the items required by the questions. And please do not forget to include the actual state leaving the turbine in our TS diagram.